Still in the standard maximum section, have your steps sitting next to you so you can kind of go through those as we walk through this. Here, notice that we're looking at a larger system, so we can't actually do the graph. We also have different looking variables. So instead of x, y, z, they're calling it x1, x2, and x3. You notice that we are maximizing the objective function, so that satisfies the first piece of criteria for a standard maximum. Also notice that the inequalities, the constraints, all have less than or equal to. That's the next criteria to satisfy. Also, the constants must be non-negative, and also the variables all must be non-negative. So we've satisfied all the criteria to be a standard maximum problem. So we can use the simplex method process we just talked about. The first thing to remember is to introduce the slack variables. We want to start with the first inequality and take up the slack. So 5x1 minus x2 plus x3 plus s1 is equal to 1500. So we took the less than, we added some more in to make it equal to 1500. Now we're going to take 2x1 plus 2x2 plus x3. The second slack variable may need to be different than the first one, so let's call it slack variable 2, S2, and that's going to take up the slack from being less than to making it equal to. And then taking 4x1 plus 2x2 plus x3. Again, may be different from S1 and S2, so the third slack variable would be S3. We're going to add that to make it equal 2000 instead of being less than. And we don't do anything to these variables, but we do have to change the objective function. Remember, p stays where it's at because the coefficient has to be a positive 1. We just move the x1, x2, and x3 over to the other side. So subtract 3x1, subtract 4x2, subtract 6x3, and then keep the p on the same side, so don't move it, and that leaves you with 0 on the right side. And I've gone ahead and filled everything in. The key to being successful with this simplex method is keeping everything lined up. Very, very important. So let's go ahead and put our coefficients down. We've got a 5 in front of x1. You can do the whole equation if you want to, or you can go down the column. Let's just go down the column. So 5, 2, 4, negative 3. And then negative 1, 2, 2, negative 4. And then for the x3s, we've got 1, 1, 1, negative 6. And then go down with the S1. So there's only an S1 in the first equation. Zeros everywhere else. The S2 is only in the second equation, so zeros everywhere else. The S3 is only in the third equation, so zeros everywhere else. And the P is only in the fourth equation. That's your objective function. So zeros everywhere else. And our constants always go to the right of the augmented bar. So 1500, 2500, 2000, and 0. So you can label your active variables over here. Remember, they're going to correspond to those unit columns. So S1 has a 1 in the first row, which means S1 would go in the first row. S2 has a 1 in the second row, so that means S2 would go in the second row. S3 has a 1 in the third row, and P has a 1 in the fourth row. So right now our solution is that S1 is 1500, S2 is 2500, S3 is 2000, and P is equal to 0. So it's starting us out at that 0, 0, 0 because this is assuming that x1, x2, and x3 are 0 since they're not active. So that's our basic solution. But we know that profit is not going to be maximized if the profit is 0, so we need to do some pivoting here. You look at your middle section down here, you choose the most negative number. Here's my most negative. Then you go to your test ratio, A over B. So this is your A, and whatever corresponds to the most negative column, that's going to be your B. So 1500 over 1, 2500 over 1, and 2000 over 1. And we choose the smallest of those test ratios, which is the 1500. So that corresponds to row 1. So the most negative broke it down to this column, and then the smallest ratio broke it down to this row. So we're going to pivot on row 1, column 3, when we do pivot A. So this time we've got a 4 by 8. And go ahead and type in those entries. Probably a good idea to double check when you're finished. And I like to go back through my columns to check. All right, so things look good. We're going to quit that and we're going to call out Program Pivota. So hit Enter and hit Enter one more time. And then let's do row 1, Enter, and column 3, Enter. See what we've got. Go ahead and copy that down from your calculator. For X1 column, I've got 5, -3, -1, and 27. For X2, I've got -1, 3, 3, and -10. For X3, we've got a unit column. For S1, we've got 1, -1, -1, and 6. We've got a unit column for S2, a unit column for S3, and a unit column for P. And then I'm going to arrow over to get my constants. We've got 1,500, 1,000, 500, and 9,000. So P, the value of P jumped from 0 to 9,000 in this one pivot. And let's see which variables are active. So we look at the unit columns, and we've got one more here. So it looks like X3 is active in the first row. S2, because the 1 is in the second row, is active in the second row. S3 is going to be active in the third row, and P is going to be active in the fourth row. So right now our basic solution is that X3 is equal to 1,500, S2 is 1,000, S3 is 500, and then the other variables not represented here, the X1, the X2, and the S1 are equal to 0, and P is equal to 9,000. But we still have a negative here in the bottom middle section, which means we're not done yet. So we're going to use this as our pivot column, and then we're going to do test ratio A over B, where this is my A, and then whatever column corresponds to that most negative is the B. So I'm going to have 1,500, but I can't pivot on a negative, so it's not going to be that one. So it's either going to be 1,000 over 3. So you can't pivot on a negative and you can't pivot on a 0. 1,000 over 3 and 500 over 3. And if it ever happens that you have a tie for one of these ratios, you just choose one. Or if you have a tie for the most negative, you just choose one. All right, but we do look like we've got a smallest value here, which would be this one. So we're going to be pivoting on row 3, column 2. So remember, don't do anything to your matrix. Your calculator's waiting on you with the ... So hit Enter, Enter, and it automatically takes you back into the program. So row 3 and column 2. And let's look at our bottom row. No negatives. It looks like we're on our final tableau. So no negatives at the bottom. That means that you're finished. So let's write that down. We've got 14 over 3, -2, -1/3, 71/3. We've got a unit column for X2, 0, 0, 1, 0. We've got a unit column for X3, 1, 0, 0, 0. We've got for S1, 2/3, 0, -1/3, and 8/3. Looks like we've got a unit column for S2 That's the 0, 1, 0, 0. And then for S3, we've got 1/3, -1, 1/3, and 10/3. For P, we're always going to have a unit column. It's never going to change, but like I said, it's a nice little placeholder. And then we've got our values, our constants at the end. So we've got 5,000, I'm going to move that over. 5,000 over 3, 500, 500 over 3, and 10,666.66 repeating. So I believe in this one, if we were looking at dollars, we would have $10,666.67 for the profit. So let's look at our active variables. Notice here we've got a unit column, we've got a unit column, we've got a unit column, we've got a unit column. You don't have to circle those, but it helps some people. The 1 for X2 is in the 3rd row, so don't put X2 up here. It needs to go where that 1 is. The X3 has a 1 here in the 1st row. The S2 has a 1 in the 2nd row. And then, of course, P is always going to be down here at the bottom. It's where the 1 is. So let's read off our solution. The optimal solution, and let's not include the slack variables in the actual solution. Let's just do the x1, x2, s3. So x1 is not listed here. That means that x1 is equal to 0. x2 we can read off as equal to 500 over 3. And then x3 is equal to, looking at the top, 5,000 over 3. Sorry, I didn't leave you enough room right there. And then this would probably be an ordered triple. As such, and then the optimal value would be the 10,666.67 approximately. Usually WebAssign wants you to round to 2 places, but if it asks for exact, you could do the fractional form. So this means that anything that's not active is inactive, and all the inactives are equal to 0 in the optimal solution. So we have x1, of course, is equal to 0 because it's not active, and then we also know that s1 is 0 and s3, because it's not active, is equal to 0. And we know that s2, we could include that too. It's a slack variable, is equal to 500. So this is the optimal solution, and this is what's left over. So sometimes these slack variables represent different constraints, like maybe labor hours or some kind of materials in making a product. So you may not use all of the materials. Some key points to keep in mind: the pivot element must be positive. Cannot be negative, cannot be 0. Can't be negative, can't be 0. If there is not a positive number in the middle section of the pivot column, in other words, no pivot element, then there is no optimal solution. If there is a tie for the most negative number in the bottom row, I mentioned this during the example, then you just choose one. What this normally means is that there's going to be more than one optimal solution. But WebAssign, we're not going to have to deal with the infinitely many solutions case. We're just going to have to be able to type in one solution. The same thing's going to happen if there's a tie for the smallest ratio. Then you just choose one. And that means the same thing. So as I mentioned here, these are situations that can lead to the linear programming problem having more than one optimal solution. There will be infinitely many solutions if the middle section of the bottom row contains a 0 in a column that is not a unit column. So remember, those unit columns help us read off the active variables, but if we have a 0 in that bottom middle section, then that means that we can have infinitely many solutions. Or if possibly the final tableau contains 2 or more identical unit columns. And again, you really won't have to be too concerned with the infinitely many case.